Welcome to Electronics Made Cool Again. Today, we are cracking open the secret that powers, and I mean literally everything in your digital life. Your phone, your car, your watch, you name it. We're talking about semiconductors. And to really get why they're so magical, we've got to jump in a time machine.
All right, picture this. It's 1971. Intel just dropped the 4004 microprocessor. And this quote right here, it just puts into perspective how absolutely mind-blowing this was. A computer that used to take up an entire desk, costing what would be millions of dollars today, was suddenly shrunk down into one single tiny chip.
And what's really wild to me is the sheer scale of this leap. I mean, look at this. On one side, you've got a giant, power-guzzling, insanely expensive machine. And on the other, a chip smaller than your pinky nail, packed with over 2,000 transistors that basically kick-started the entire portable electronics revolution we live in today. So that leads to the big question. How in the world did they do that? How did we shrink a whole room onto a speck of dust?
To get our answer, we've got to zoom in, like way in. It's kind of like peeling back the layers of an onion. We're going to start with the chip itself and see what's inside.
Okay, the first huge idea was something called the monolithic integrated circuit. And that word, monolith, is everything. It literally means single stone. See, before this, circuits were these clunky hybrid things. You had all these separate components that had to be painstakingly wired together by hand. The absolute genius of the monolithic idea was to build everything, all the transistors, all the connections, the whole shebang, on one single solid piece of material. That was the game changer. That was step one to making things tiny.
And this wasn't some single eureka moment out of nowhere. No way. It was this rapid-fire series of breakthroughs, one building on the next. In '57, we figured out how to basically print circuits using light. That's lithography. Then in '59 came the single stone idea we just talked about. A year later, the planar process gave us a way to build these circuits in flat, stackable layers. And then by '63, we had CMOS, the super low-power transistor design that is, believe it or not, still the foundation of almost all modern electronics.
You see, all of these incredible inventions were really about one thing: figuring out how to build a city of microscopic electrical switches. We call them transistors, all on that one single stone. So the next obvious question is, what is this magical stone made of that lets us do that?
And here it is. Meet the unsung hero of our entire story, silicon. It's not just super common, it turns out it's almost perfect for this job. And the reason for that? Well, it all comes down to its beautiful atomic structure.
So what makes silicon the chosen one? Well, when you get it really pure, it forms a near-perfect crystal. Its diamond lattice structure means every single atom lines up in this perfectly ordered, predictable grid. It's incredibly dense. We're talking 15,000 billion atoms in a space the size of a sugar cube. And because it's the second most common element on Earth, it's abundant and cheap. This perfect structure gives us a pristine, flawless canvas to build on. Let's try to visualize that for a second. Imagine a perfect cube made of atoms. Now, imagine taking a second, identical cube and meshing it perfectly inside the first one. That's pretty much silicon's diamond lattice. This structure isn't just super stable, it's so uniform and so predictable that we can start to manipulate its electrical properties with unbelievable precision. And that is the real secret to making a rock think.
All right, so we've got our perfect crystal canvas. But how do you actually turn a piece of purified sand into billions of tiny on-off switches? The answer lies in a really cool physics concept called the band gap. So every material has this thing called an energy band gap. Just think of it like a hurdle that electrons have to jump over for electricity to flow. In a conductor, like a copper wire, there's basically no hurdle. Electrons just flow freely. It's always on. In an insulator, like glass, that hurdle is a giant wall. Electrons can't jump it. It's always off. But here's the magic. Semiconductors, like silicon, they have a small, manageable hurdle, and that is their superpower. It means we can give electrons just a little push to get them over the hurdle, turning the material from an insulator into a conductor whenever we want.
Which, leads us right to the next big question. If we can give electrons that push to cross the gap and turn the switch on, how exactly do we do that?
The technique is called doping. And honestly, it's kind of like precision cooking. You start with your ultra-pure silicon crystal, which on its own doesn't really conduct electricity. Then you intentionally mix in a tiny, perfectly controlled amount of impurities, other atoms like phosphorus or boron. These new atoms don't quite fit in the perfect silicon lattice. They either bring an extra electron along for the ride, or they create a hole where an electron should be. And these extra electrons or holes are what let the electricity start to flow.
And this is where things get really, really clever. Because by creating two different flavors of this doped silicon and then sticking them together, we can build the single most important fundamental component in all of electronics.
Okay, let's break it down. If we dope silicon with phosphorus, we get extra electrons. Since electrons have a negative charge, we call it N-type silicon. Easy enough. If we use boron instead, we get a deficit of electrons. These holes act like positive charges, so we call it P-type silicon. Simple, right? Now for the fun part. What happens when we join them?
The instant that N-type and P-type silicon touch, something amazing happens. All those extra electrons from the N side immediately rush over to fill the empty holes on the P side. This mashup creates a thin barrier right at the junction called the depletion region, which has its own built-in electric field. And that field is the whole point. It acts like a one-way valve for electricity. It lets current flow easily in one direction, but slams the door shut if it tries to go the other way. This simple PN junction is the world's tiniest one-way street, and it's the heart of pretty much every diode and transistor ever made.
Okay, deep breath. We've just zoomed all the way down to the atomic level. So now, let's zoom back out and connect this incredible little building block to that revolutionary microprocessor we started this whole journey with.
And there it is. That's the connection that changes the entire world. The PN junction is the simple little mechanism that lets us control electricity. A transistor is just a clever sandwich of these junctions that lets us turn that control into an on-off switch. And a microprocessor? It's just a massive, mind-bogglingly complex city built from billions of those tiny switches.
And this ability to just keep cramming more and more switches onto a single piece of silicon led to this incredible phenomenon of exponential growth. This progress, famously predicted by an observation called Moore's Law, has just been relentless. We went from thousands of transistors in the 70s to millions in the 90s to the absolutely staggering numbers we see on chips today.
Seriously, just let that number sink in for a second. Over 50 billion. We went from the 2,300 transistors in that first ever Intel chip to tens of billions of switches, all firing in perfect harmony on a chip that's about the same size. It is an almost unimaginable leap in power, and it was all made possible by understanding the physics of a single, perfect stone.
So now we get it. We understand this secret. From a perfect crystal structure to a manageable band gap to doping and finally to the PN junction, we've basically unlocked the fundamental principles that power our entire modern world. But it leaves us with one last fascinating question. As these switches get so small they're approaching the size of just a few atoms, how much further can this revolution actually go before we just run out of room?